Hello, everyone. We would like to give you some feedback on that first project and first assignment that we had, which is to determine the stiffness matrix of the shown truss. Basically, that was the first step. And then afterwards, after you come up with that stiffness matrix of the truss, we have the loading applied to the truss, and we wanted to get the reactions. And more importantly, we would like to get the forces in the members. And I noticed in almost all the submittals that you were missing the force in the members. So let's go through that very quickly. That truss that you're seeing right here has a pin support that has two unknown reactions, and you have a roller or a bearing support that has only one unknown. So you have three unknown reactions, and we know the degrees of equations is three. So it looks to me like it's statically determined externally. But look closely, is it statically indeterminate to the first degree or not? Just check this, trust. But it's not going to change anything from what we are doing as far as the stiffness matrix. So how do we approach that? We start with numbering the joints and numbering the members, as you recall, which is exactly what we've been doing before. And as you can see here, we number the joints 1, 2, 3, and 4, and we put the degrees of freedoms. And as you can see that we have 4 nodes, so we will have 8 degrees of freedom. And we're going to start numbering the unconstrained displacements first. So if you look closely here, we have freedom right there, 1, 2, freedom at that joint as well, so it'll be 3 and 4, and then freedom at that roller support, 5. Anything else which is 6, 7, and 8 are constrained. That's how we do it. And then we start for member 1, and the near and the far, and we establish lambdas, and we establish that stiffness matrix for member 1. We go to the next member, which is member number 2, and we do the same exact thing. We have the lambdas, and we have the K for member 2. We repeat that for member 3, and we're done here with 1, with 2, with 3, and we do it for 4 and 5, as you can see here in the next slide. So we were done with all this stiffness matrix for the 5 members. We assemble them together. And when you assemble all this, you're going to end up with an 8 by 8 stiffness matrix. So I assume that you are familiar with that. We're going to have 8 by 8 stiffness matrix, so that shouldn't be a problem. Here is how you assemble them. The 6 members, I'm sorry, I think I forgot one. So it's 1, 2, 3, 4, 5, 6. And then you assemble them to be 8 by 8 stiffness matrix. I assume that the majority of you who submitted their assignments or the project, they have that, and that shouldn't be a problem. I'm still missing 3 students that did not submit. So please just communicate with me to see what's happening. After that, we would like to do the partitioning, and we would like to get this displacement and all this stuff. And I'm glad that you were able to identify the loads which are at the degrees of freedom. So we were able to find out that you have -4 and you have 2, and these are the forces that you are going to be dealing with, and these are the known forces. So if you look closely at the degrees of freedom 1, we don't have any force, so that's 0. Here we go. And degrees of freedom 2, the same thing, 0. Degrees of freedom 3, you have 2. Degrees of freedom 4, you have -4. Degrees of freedom 5, you have no force applied. So this is the vector or the matrix of the forces, 0, 0, 2, -4, and 0. We agree. But we still are missing 3 others, which is the support reactions, which is at that node at degree of freedom 6, degree of freedom 7, degree of freedom 8. Again, to summarize, we have 5 known forces and 3 unknown reactions. On the other hand, these are the known displacements, as you can see. Is it here at this node? No. Is it here at this node? No. It's actually at these 2 nodes. At that node, we have 7 and 8. There are zeros because it's a pin support, not allowing any horizontal or vertical movement. At that roller support, it's allowing that kind of vertical movement, but it's preventing the horizontal. So that's why we have 0, 0, 0, 6, 7, 8, which is 0, 0 right here at 6, 0 right here at 7, 0 at here at 8, which is showing the degrees of freedom. Now we would like to solve that. So we're gonna establish the stiffness matrix as you can see right here. And basically when you do that, you are able to, I'm just trying to make this bigger a little bit so that it will take the whole picture. We would like to get the stiffness matrix as you can see right here, and you're saying that the force equals K times D, and you do that partitioning and you solve for that part right here. So this is the first part that you solved for, 0, 0, 2, -4, and 0, and you put it here on the side, and basically equals to the K times D1 to D5, which is from D1 to D5. Again, I usually draw a line right there after the fifth row, and I draw another line here after the fifth column, and that is the partition. I can simply say that the left-hand side is known right here, the right-hand side here, D1 is unknown, so we can find D1. Similarly, you find D2 all the way up to D5. And you were all able to do that, the majority of you who submitted your assignments, and you were able to find the distance, or rather the displacements that we're having from D1 to D5, and that is perfect. So after you came up with this displacement, you can go back to the matrix, which is in the previous slide right there. You go to the second part of the matrix right here, which is Q6, Q7, Q8, and you will be able to find this support reactions. You end up with -4, 2, and 4, and start examining that. What does that mean, -4 right here? Basically, that is opposite to whatever we assumed, and we have 2 at degree of freedom 7 and 4 at degrees of freedom 8. We're good with that. And you all stopped at that. What did you guys forget? Almost all of you, I have never seen I didn't see the answer for the force member. So after you came up with displacement, after you came up with the reactions, you stopped right there. And you're just lacking that last part here, which is in blue color, which is the force in the member using this kind of equation. And you just simply, you will find out the force in one of the members, which is member 2, for instance. You apply this equation knowing the displacements that you're having, so you will be able to find out that the force is 2.56 kips. And I would greatly appreciate if you guys can revisit that, and in the future for the final project, if we're gonna deal with trusses again, just that is the last step that you need to identify, which is using this formula, which is the Q equals AE over L, and then the deltas, and multiply that by the displacements, which is the displacement near at X, displacement near at Y, displacement far at X, displacement far at Y, and you will be able to find that. I hope that helped, and I'm in the process of going through your project right now, and I only received 4 submittals for the projects, and some of them are lacking the sound, some of them are lacking the videos, which is okay if you'd like to submit an narrated PowerPoint presentation or an impressive PowerPoint presentation. So good job, guys. Keep it up, and I will update you shortly with your project grade. And for those of you who did not submit the assignment 1, assignment 2, and project 1, please communicate with me to see what we can do. Thank you so much and have a great day.